Welcome. This podcast is on the topic of ratio and proportion, and we'll begin right away. A ratio is a comparison of two numbers. For example, I could say I could compare the number 3 to 5, and I would simply write it as 3 to 5, and that would be a ratio. In the nursing department, instead of writing the word 2, they use a colon, 3:5, to represent that ratio. And that comparison is usually done by division in a math class. So in a math class, you can think of a ratio as being a quotient, like 3 to 5, written that way. You could call that per, 3 per 5. But another way that people often refer to it is out of. 3 out of 5 represents a quotient in math. Now, if I attach units to that ratio, I get what is called a rate. So let's say that I come over here with my 3 to 5 and I call it 3 gallons per 5 minutes. Then that would be a pumping rate for a pump. I could say that my pump pumps 3 gallons every 5 minutes, or 3/5 of a gallon per minute. Or I could use like 60 feet per 5 seconds. There's a ratio, but it has units attached, so it's a rate, and that particular rate is a rate of speed. It's equal to 12, because 60 over 5 is 12 feet per second, and you recognize feet per second as a speed measure. So a pure ratio is just a comparison of numbers. When you add units to it, we call it a rate. Now, certain rates can be converted to pure ratios, and that happens whenever the top unit is similar to the bottom unit. So if I had the ratio or the rate 5.5 minutes per 60 seconds, both of those are time units. If the top and the bottom units are the same type of unit, like if they were both money units, or in this case both time units, minutes and seconds, then you can get rid of those units with an appropriate adjustment. Since there's 60 seconds in 1 minute, 5 minutes would be 300 seconds. Another half minute would be another 30 seconds. So that would be the same as 330 seconds on the top. Now when you put your 60 seconds on the bottom, you can see that the units go away. The seconds cancel the seconds. The 10 cancels the 10. The 3 cancels the 3. And I end up with the pure ratio 11 halves. Now, what does that mean for us? Well, for us, that means that if you have a pure ratio with no units showing, it's the same as having the units on the top be equal to the units on the bottom. So I could take my 11 over 2 and I could change it to feet on the top, feet on the bottom, and that's the same as a pure ratio because I can just cancel the feet, and then I have the pure ratio 11 over 2. Well, with that background, the distinction between a ratio and a rate, let's move on and see how ratios can be used. In this first example, we're going to use the ratio, a definition of a certain ratio, to establish a physical constant called the coefficient of friction. Example 1. The coefficient of friction is the ratio of the force required to overcome friction to the force pushing two objects together. If it takes a force of 450 newtons to move a 1.1 kilonewton box across the floor, what is the coefficient of friction between the box and the floor? Well, let's go back to the original setup. It said the coefficient of friction is the ratio of the force required to overcome friction. If I push on the box with less than 450 newtons, it doesn't move. It says here it takes a force of 450 to get that box to move. So the force required to overcome friction is 450 newtons. Now if I want the ratio of that force to the force pushing the item against the floor, that's the force 1.1 kilonewtons, because that's the weight of the box. And the weight of the box means the force with which the box is being pushed to the floor by gravity. So, or I should say pulled to the floor by gravity. And that is 1.1 kilonewtons. Now if I put 450 over newtons over kilonewtons, the newtons cancel. So I end up with 450 over 1.1, and kilo means times 10 to the 3, so that's 1.1 times 10 to the 3. And that ratio comes out to be 0.409. If you pop that in your calculator. And since both of those were two-digit numbers, if we were using rounding rules, that would be 0.41. So the coefficient of friction between this particular box, whatever material it's made of, and the floor was 0.41. Now, what we're going to be using is less pure ratios than something called proportions. A proportion is a sentence stating that two ratios or rates are equal to each other. So if I had the sentence like this, 5/11 equals 1/2, technically that would be a proportion. However, it's not true, is it? 5/10 is equal to 1/2. So we would call this a false proportion. Some books say it's not a proportion because the ratio is not truly equal. Doesn't matter which one you do. You can say it is a proportion, but it's false, or you can say it's not a proportion. That's just a language technicality. Now, the second part of the definition says proportions are true if and only if the cross products are equal. The cross products are the products you get if you make a cross through the equal sign. So one product here would be 5 times 2. That gives you 10. The other cross product would be 11 times 1. That gives you 11. Since the cross products are not equal, that's not a true proportion. But look what happens if we make it a true proportion. I do again the cross products. This time I get 5 times 2 equals 10 times 1. That is true, so we call that a true proportion. We call this a true proportion, this original statement that those were equal. So how can we use that to solve problems? Well, that comes into play whenever something in the problem establishes that a certain ratio or rate is going to hold as true throughout the problem. So let's take an example of such a problem. Here's example 2. It says the atomic mass of carbon is 12 units, where units just means something called an atomic mass unit, which is a physical constant. So continuing on with our problem, the atomic mass unit of carbon is 12 units. If the ratio of the atomic mass of carbon to the atomic mass of oxygen is 4 to 5, what is the atomic mass of oxygen? Well, right here, I established the ratio 4 to 5 as being constant through this problem. It's the ratio of the atomic mass of carbon to the atomic mass of oxygen. So I'm going to set up a proportion now with this, and it'll go like this. 4/5 is the same as the atomic mass of carbon to the atomic mass of oxygen, which I'm just going to call X. So X is the atomic mass of oxygen. And now that I've set up that proportion, and I know that it's true because I was given in the problem that that ratio is 4/5, so I know that these are really equal, then I can find the value X by setting the cross products equal. So I go ahead and do that. I get 4X for the first cross product. I get 5 times 12 for the second cross product, or 60. And so if I divide both sides by 4 here, I get 4x over 4 equals 60 over 4. The 4's cancel on the left. 60 over 4 is 15. So I get the atomic mass of oxygen is 15. Let's try another problem. In the second problem, we can find that there's more than one way to solve some of these ratio proportion problems. We'll take a look at a couple of ways to do this one. If a drug is prescribed at the rate of 1.5 ounces of medication for each 120 pounds of patient's weight, how many additional ounces would be needed for a patient who weighed 160 pounds? And that should be a question mark there. So I'll change that to a question mark. And we just, in the first sentence, we established a ratio or rate to remain constant throughout the problem. We said that 1.5 ounces, or 1 1/2 ounces, is used for 120 pounds. So that establishes the medication use ratio, 1 1/2 ounces per 120 pounds, which has to remain constant. So then how do you set up the other side to solve how many additional ounces would be needed? Now, this is kind of a tricky question because it doesn't say how many ounces would be needed. In our ratio, 1 1/2 ounces is the number of ounces needed for a 120 pound patient. Our question is asking how many additional ounces would be needed. How many ounces past the 1 1/2 ounces? So here's where you can take the two different approaches to the problem. In the first approach, I could say, let X be the number of ounces needed. Since I want the number of additional ounces, I could just solve for X, then subtract 1 1/2, and that would give me the additional ounces. So I'll set it up that way. How many ounces are needed for a 160 pound person? Notice that the setup of units is exactly the same. Ounces per pound on the left, ounces per pound on the right. Once those units are established on the left, you must keep the same units on the right. Otherwise, this ratio has no chance of being true. Okay, I'm going to set my cross products equal here. One cross product is 1 1/2, or 3/2, times 160. The other cross product is 120 times X. Here I cancel the 2 with the 2 and the 160 to give me 80. So I end up with 240 is equal to 120X. To get X, I divide both sides by 120. On the right side, they cancel and leave me X. On the left side, 240 over 120 is 2. So I get 2 ounces of medication for a 160 pound patient. Well, if 2 ounces are needed, and if 1 1/2 ounces were needed for a 120 pound patient, then 2 minus 1 1/2, 1 1/2, which is 1/2 ounce, would be the additional medication required for the 160 pound patient. Now, I could have set it up that way in the beginning so that I didn't have to do this conversion when I got to the end of the problem. I could have said let X be the additional ounces needed for the 160 pound patient, and then the total ounces needed would be the original ounces, 1 1/2, plus the additional X ounces. And that would give me the total ounces needed for a 160 pound patient. So I could write my ratio. My ratio would be 1 1/2 ounces is to a 120 pound patient the same as X plus 1 1/2 ounces is for a 160 pound patient. Now when I find X, I'll be through. Again, I would set my cross products equal. So I would get the same 3/2 times 160 as I had earlier. And on the other side, I'd get 120 times X plus 3/2, which if I distribute would give me 120X distribute there, and then distribute to the second term. 120 times 3 halves would be 180. Over here, the 2's cancel again, giving me 80, so I get 240 is equal to 120x plus 180. Now if I subtract 180 from both sides in an attempt to get x by itself, I get 60 equals 120x. I divide both sides by 120. 60 over 120 is a half. On the right side, the 120's cancel, so I get x equals, again, 1/2 ounce. Now this time I'm through, because I let x be what I was looking for. I let x initially be the 120, or the additional ounces needed, which is what the problem asked for. So I didn't have to do anything with x once I finished. That was the real answer. So you do a trade-off. In this problem, if you want x to be exactly what you're looking for, the setup is a little harder and the solution is a little harder. But if you just let x be the ounces needed for a 160-pound person, you get an easier setup, you get an easier solution, but in the end, x is not what you're looking for. So you have to take the x that you got, subtract the initial amount to get the additional amount. Well, let's try one more. In this problem, like an earlier problem, we have a situation in which there are going to be no units attached to one of the established ratios. Now, the problem with that is it's attaching the units that tells us how to set up the other side. So what do you do when there are no units given? Example 4 says the scale on a blueprint is 48 to 1. 48 what to 1 what? Well, we don't know, but that's the ratio that has been established as constant throughout the problem. And we discussed before what happens when you have a pure ratio with no units here. Well, what it means is the units at the top and the units at the bottom are the same. If I put here feet and feet, that's the same as just 48 to 1, because you could cancel the feet with the feet. So it says here the scale of a blueprint is 48 to 1. If a room is 4 3/4 inches in length, by 3.5 inches in width, what is the real size of the room? Well, you might be tempted here to want to put 3.5 over 4 3/8, but that's not really a ratio or rate that's the same throughout the blueprint. That ratio or rate only holds for that one room. The established ratio or rate for the whole blueprint is this original ratio, 48 to 1. So what we're going to do is we're not going to try to establish a ratio between the length and width. That's not a constant ratio. We'll use our constant ratio to establish the length, and then we'll use it a second time to establish the width. So I have 48 to 1. Now, when you don't have any units, stick something in there to serve as units. So I'm going to say 48 real to 1 drawing. That means 1 unit on the drawing is 48 of those units on the ground, and that's assuming that the blueprint's smaller than a house. I'm sure it is. It'd be hard to carry around a blueprint that was bigger than a house. So you can figure that the 48 goes to the real object, the house part, and the 1 is the part of the ratio that goes to the drawing. Well, let's say that we want to establish the width of the room. We know that the room is 3.5 inches wide on the drawing. Whoops. Now that's the width drawing. I got to be careful here. Notice I've set up on the left real is to drawing. So I'm going to say x inches real is to 3.5 inches on the drawing. So that's why you establish these units here. When you establish which is real and which is drawing, it tells you how to set up the right side. I know that I have to have the real units on the top, the drawing units on the bottom. Okay, I set my cross products equal. This time I just get 1 times x, which is x. This is 48 times, and then 3.5 is the same as 7/2, so I'll just do this in fraction form. So I get 24 times 7, which is 168 inches. Well, that's a lot of inches. You'd certainly want to convert that to feet. If you do a inches to feet conversion, you simply divide by 12, so that's 168 divided by 12 on your calculator. 168 divided by 12 turns out to be 14, so this would be 14 feet. Would be the width of the room. To get the length of the room, you just simply do it again. 48 on the real to 1 on the drawing is the same as 4 3/4 inches on the real. No, sorry, that's the drawing again. So you got to be real careful. That's the importance of setting those units up. That's x inches in the real to 4 3/4 inches on the drawing. Now you simply, I think I said 4 3/8 up there. Should have been 4 3/4. So we set our cross products equal. We get 48 times, and 4 3/4 would be 19/4 is equal to x. The 4 cancels the 4 and the 48 to give me a 12. So 12 times 19 is okay. Let's just leave it like that. 12 times 19 inches is x, and if I wanted to change that to feet, I'd take 12 times 19 inches. Using my conversion factors, I'd multiply it by 1 foot per 12 inches, and the 12s would cancel, and so I would get 19 feet. So the room that we are looking at would be 14 feet in width by 19 feet in length. And there's an example of using ratio and proportion. When your original ratio has no units attached, you attach some units, and that'll tell you how to set up the other side and give you the solution to your problem. And that completes our podcast.